welcome back. This is lecture 10. So in the previous class, we took a dive into the structure of a MOSFET device, which we will be using to achieve our goal of amplification, right? And we also spent some time in getting ourselves familiarized with the current voltage equations of a MOSFET. So quickly a recap. So if this is our N MOSFET and these terminals are marked as gate, drain and source, and the current between the drain and source, if we mark it as IDS, right, what do we get? We get the fact that IDS is equal to, there are three regions of operation. So IDS is equal to 0 when VGS is less than the threshold voltage, right? And IDS is equal to mu n C. Mu n C ox W over L VGS minus threshold voltage times VDS minus half of VDS squared. This is when, of course, VGS has to be greater than threshold voltage, but an additional condition needs to be satisfied. And what is that? That VDS should be less than VGS minus the threshold voltage. And we have one more region of operation, which is where the current is half mu n C ox VGS minus threshold voltage whole square, under the condition that, of course, again VGS has to be greater than threshold voltage and VDS has to be greater than or equal to VGS minus the threshold voltage, right? The other thing that we didn't touch upon was what about this current? What about the current that is going into the gate? What about IG? Now note that if we go back to the previous lecture, if we go back to lecture 9, what we saw is that the MOSFET structure, right, by the way the MOSFET is made, we have a oxide or an insulator between the gate and the channel, right? So these parallel lines in a MOSFET symbol essentially symbolizes the fact that there is a capacitance between the gate, wherever you have the gate terminal, and wherever you have the channel, that is the other side of the capacitance. So naturally the DC current, DC IG, is always equal to 0 regardless of any other condition, right? So then IG is equal to 0 always at DC. Okay, so now if these are the complete current voltage characteristics or complete current voltage DC characteristics of a MOSFET, how does this help us? How does this help us in achieving amplification? That's the moot question, right? That's what we are after. So if before stepping into answering that, what we will do is we will plot this current voltage characteristics just like we plotted the current voltage characteristics of a two-port network, from where we hypothesized that the two-port network needs to have certain type of characteristics in order to give us amplification of power, right? So we need to now, so what we will do next is we will we will sketch the IV characteristics of this MOSFET, because this MOSFET in itself can behave like a two-port network, and we will see whether this satisfies our requirement, right? So what we'll do, so let's mark the terminals properly first. So let's say, so this is the box, right? This is the box. This is one port. This is one terminal that comes out. One terminal is common. This terminal. The first port is this. The second port is this, right? And we call this V2, and we call this V1. This current that is going into port 1, we call this I1, and this current that is going in to port 2, we call this I2. Now note that now that we know that this is a MOSFET inside, what do we know? This I1 is always equal to 0, and I2 is essentially IDS, right? And V2 is VDS. And what is V1? V1 is VGS. Okay. So now that we know many things about a MOSFET, let's quickly sketch out the current voltage characteristics. So what will be I1 versus V1? I1 versus anything is essentially 0, right? So I1 is always 0. So I do not have to plot the first two characteristics, right? I do not have to plot I1 versus V1 and I1 versus I2, which naturally means that Y11 is equal to 0 and Y12 is equal to 0. So since I1 equal to 0, these are the natural consequences, right? So we are off to a good start, because what we expected from an ideal two-port is the fact that I should have Y1 equal to 0 and Y12 should also be equal to 0. So what are the other two things that we need to bother about? Y21 and Y22, right? So how do I get Y21? From which plot should I get Y21? Y21, in order to get Y21, I need to find out the current voltage relationship between I2 and V1, right? I need to find out the relationship between I2 and V1. Now what is I2 for a MOSFET? By the way, we have sketched I2 is nothing but IDS. And what is V1? V1 is nothing but VGS, right? So what is the current voltage equation? That is, what is the relationship between IDS and VGS? Now you might turn around and say that, hey, I mean, there are two equations governing my relationship between VGS and IDS. Which one should I plot, right? So what are these equations and under what conditions are they valid? Firstly, if we start from VGS to be equal to 0, let's assume the threshold voltage is positive. Let's assume threshold voltage is positive. So let's assume VTH is greater than 0, right? So let's say I mark off a point VTH on the x-axis. So what can you comment? What will be the current when V1 is less than VTH? The current is absolutely 0. So that is an easy part, right? So we'll have 0 current, no problem. What happens after I increase VGS beyond the threshold voltage? If I increase VGS just beyond threshold voltage, you might turn around and ask me, That is not a sufficient information. You need to tell me what is VDS, what is the voltage difference between the drain and the source, so that I can understand which equation I should use, right? Okay, let's take some numbers. So let's assume VTH is equal to 1 volt. So this is 1 volt. And let's further assume some value of the drain voltage, right? Let's assume VDS is equal to 3 volt. Okay, so now what can you comment on? What can you comment on when my VGS is just above 1 volt? When VGS is just above 1 volt, then what is VGS minus VTH? VGS minus VTH is close to 0. So VDS is greater than VGS minus VTH, right? So I will be in saturation region of operation, right? I will be in saturation region of operation. So this equation will hold. Correct? If that equation holds, what should my curve look like? It should look like a parabola, right? So this should look like a parabola. So what is this equation? This equation is half mu n C ox W over L VGS minus threshold voltage whole squared, right? So till what value of VGS I should be able to, or rather the question is, till what value of VGS will this parabola persist? If I keep on increasing VGS till infinity, will this keep on going? Obviously no, because you must have already figured out that when I am increasing VGS, what am I doing? I am going closer and closer to the condition of VDS is equal to VGS minus VT, right? In other words, saturation region is true, right? So this equation is valid. What is the validity of this equation? This equation is valid as long as VDS is greater than equal to VGS minus threshold voltage. What is VDS in our case? In our case, VDS is 3 volt, which means this will be true as long as VGS is less than equal to VDS plus threshold voltage, that is 4 volt, right? So till, if I mark off, like if this is 1, this is 2, this is 3, this is 4, right? If I mark off 4 volt here, so this parabola, let me remark them, otherwise I will run out of space. So let's say this is 1 volt, this is 2 volt, this is 3 volt, this is 4 volt, right? So it was 0, then it became a parabola and it went like this. This is 4 volt, this is 1 volt, VGS. Then what will happen? Which equation will take over? Which equation will take over? Clearly, the linear region equation will take over, the equation 1 will take over, and in equation 1, what can you comment? What is the relationship? What is the type of relationship between the current and VGS? It's a linear relationship, right? So from here on, the current will increase linearly, right? So this will be mu n C ox W over L VGS minus VTH times VDS half VDS squared, right? So that will be the linear region condition. Note that this curve is valid as long as VDS is held constant. You have a battery between the drain and the source, constant at 4 volt, right? So this is for VDS is equal to 4 volt. Now let's say I increase VDS from 4 volt to 4.1 volt. What do you think is going to happen? So let's say I increase VDS from 4 volt to 4.1 volt. What do you think is going to happen to the curve? What do you think will happen to the saturation region curve? You must have already figured it out that the saturation region current equation is independent of VDS, which means there will be absolutely no change as far as the saturation region condition is concerned. However, what's going to happen to the linear region condition? In the linear region condition, the current is going to change. It will increase or decrease. It will increase simply because, initially it will start increasing because when you increase your VDS, right? If you stare at this equation, you will see that beyond when you are in linear region, right? When VDS is less than VGS minus VTH, when you increase VDS, your current increases, right? So which means you'll have a slightly, it will still be linear, the slope will still be linear, the curve will still be linear with respect to VGS, but it will be a steeper slope. Okay, fine. So now this is as far as my I2 versus V1 or IDS versus VGS curve is concerned. This is the large signal plot of I2 versus V1 or I2 versus VGS, but we are interested in incremental Y parameter, right? We are interested in Y21. So what is Y21? Y21 is nothing but del I2 del V1, obviously under the condition that V2 is constant or VDS is constant in this case. So this is nothing but del IDS del VGS, which is mu n Cox W over L VGS minus threshold voltage, right? This is under saturation condition, right? This is under saturation. This is when, for as long as VDS is greater than equal to VGS minus threshold voltage. What about the case? What about the case when I have reached the limit? I have kept on. Okay, sorry, I made a mistake here. Some of you might have already figured it out. Let me correct the mistake before I go ahead. So what mistake did I do? When I went from 4 volt to 4.1 volt, right? I'd like to draw your attention to this curve that we drew. When we went from 4 volt to 4.1 volt, right? What is the cutoff frequency for threshold? What is the new cutoff frequency for threshold? It's not, sorry. So this was for VDS is equal to 3 volt, and I should have said what's going to happen for VDS equal to 3.1 volt. Beg your pardon. Apologies for the mistake. So now the question that I'm asking is that how should that curve that I drew, the blue curve, look like when I change from VDS equal to 3 volt to VDS equal to 3.1 volt? Clearly the saturation region current wouldn't have changed, right? But what about the limit of saturation region? Should it change? Obviously it should change, because note that the limit of saturation region is this. If the VDS has changed, then the limit of saturation region should also have changed, which means the new limit should have been 4.1 volt, right? The new limit should have been 4.1 volt, which means this current should have continued increasing till 4.1 volt and then should have started to linearize, right? Okay, so given that we corrected that in time, let me ask you this: what's going to be my Y21 when I am in that linear region of operation? It's straightforward, so we can simply do Y21 is equal to del IDS del VGS in linear region, which will be nothing but mu n C ox W over L times VDS. Okay. Now, can you comment on which Y21 is higher, the Y21 in saturation region or Y21 in linear region? Now note that this also has a limit. The limit is VDS is less than VGS minus the threshold voltage, right? So clearly the Y21 in saturation region is higher, right? Because even though this equation is telling you that it might look like if I keep on increasing VDS, Y21 will increase, right? I mean, when you are in linear region, you can, if you keep on increasing VDS, you will hit saturation region and you will switch over from this equation to this equation, right? You will switch over from the bottom equation to the top equation, and naturally, which means that you are switching over from one region of operation to the other region of operation. So clearly you always get, at least from the equations that the governing equations that we are using, you will always get higher Y21. You will get higher Y21 as long as you are in saturation region. Now, if I take you back few lectures, if we take you few lectures back, what is the expected Y21? What is our wish list? What is our wish list for a good amplifier? Y21 should be as high as possible, right? Y21 should be as high as possible, which means that I would not only we need to be in saturation region, right? We need to have high W by L, we should need to have high VGS minus VTH, and so on and so forth, right? So that is as far as maximizing Y21 is concerned, right? Okay. So to maximize, so in a nutshell, to maximize Y21, we need large W over L and large, or I shouldn't say maximize, I should say to get large Y21, we need to have large W over L and large VGS minus threshold voltage, while keeping MOSFET in saturation. So this is crucial. This is crucial because so what will happen, let's say if I keep on increasing, looking at this curve, what will happen if I keep on increasing VGS minus VTH? So this portion of the curve here, so this portion of the curve denotes saturation region, and beyond this denotes linear region. So if you keep on increasing VGS minus VTH, right, what is the trouble that you are inviting? The trouble that you are inviting is you are going closer and closer to the to the edge of saturation region, right? So you can only do so much. So there in essence is a limit of how much you can increase VGS minus VTH before you run out of any voltage room, right? Okay, so we will see that these constraints will come up quite frequently as we move ahead with the course. Okay, so this is as far as the Y21 for our MOSFET is concerned. We also need to figure out what is Y22, right? So in order to figure out Y22, what should we sketch? You are right, we should sketch I2 versus V2 while keeping V1 to be constant. What is I2? Again, I2 is nothing but IDS. What is V2? V2 is nothing but VDS. We need to sketch the IDVD characteristics or IDS versus VDS characteristics while keeping V1 constant or while keeping VGS constant, right? V1 is nothing but VGS. So let's say we sketch it for VGS is equal to, let's say we sketch it for VGS equal to 2 volt. So if VGS is equal to 2 volt, right, what is that boundary of VDS, or what is the boundary of V2 when we hit where one side of the boundary you will be having linear region and other side of the boundary you will have saturation region? So clearly we need to figure that out. So the boundary is VDS should be greater than, the boundary for saturation or the condition for saturation region is VDS should be greater than VGS minus VTH. Again, threshold voltage is 1 volt. So this becomes 1 volt. So if I mark off, let's say 1 volt here, if I mark off 1 volt here, this side of the plot, right? Any side of the plot where VDS is greater than 1 volt will be saturation region, and this side will be linear region for the condition of VGS is equal to 2 volt. Okay, so which plot is easy to draw? Clearly the saturation region plot is easy to draw because in saturation region my current doesn't depend on VDS, right? So since my current doesn't depend on VDS, I can simply say that this is essentially a straight line. And let me call this ID set for VGS equal to 2 volt, right? So what is ID set? ID set is half mu n Cox. VGS is 2 volt minus threshold voltage is 1 volt whole square, which is half mu n Cox times 1, right? So whatever this value might be, so this is my ID set for VGS is equal to 1 volt. Okay, fine. What will happen when I drop from 1 volt VDS to 0, right? Essentially what I am asking is that what is going to happen in linear region. So linear region, clearly my current equation becomes mu n Cox W over L VGS minus threshold voltage times VDS minus half VDS squared, right? So let's see what will happen at very low, very small values of VDS, that is near the origin. So clearly at near the origin, so if VGS or VDS is much less than VGS minus threshold voltage, right? If this is the case, right, so I can essentially I can essentially neglect this term, and my IDS becomes mu n Cox W over L VGS minus threshold voltage times VDS, right? So which means it becomes a straight line. So near the origin, this will become a straight line, and minus half VDS square term will start picking up, will start to dominate as we go away, away from origin towards higher value of VDS. And clearly this is also a parabola, and this will essentially go and merge with the ID set, right? Okay, so far so good. What's going to happen now if I say I change the value of VGS? Let's say I go from VGS equal to 2 volt to, let's say, VGS equal to 3 volt. What's going to happen to ID sat? Clearly, ID sat will increase, and it will increase by how much? The new ID sat will be half ID sat for VGS is equal to 3 volt. Here the VGS is equal to 2 volt, right? So I made a mistake here. Please pardon me. So this for VGS equal to 3 volt will be half mu n Cox 3 minus 1 whole square, that is 4 times whatever we had earlier. So this ID sat will increase to some value. Let me call this 4 times ID sat of VGS equal to 2 volt. So this will be equal to ID sat for VGS equal to 3 volt. So this again will be constant, but now till what voltage will this be constant? What voltage of VDS will this be constant? In other words, I am asking what is the limit for which beyond which you have the demarcation line of saturation region and linear region. Clearly, if VGS is 3 volt, that line moves from 1 volt to 2 volt, right? So 3 minus 1 is 2. So that line goes here. So your saturation. So it will be flat beyond VGS equal to VDS equal to 2 volt, and after that it will dive, it will nose dive, and it will become something like this. Okay, that's great. Similarly, I mean, I can do this exercise for all values of, continuous values of VGS, as VGS as a parameter, and if I will get similar plots. I'll get one plot for lower VGS which should look like this. Similarly, I'll get a higher plot. So here, lower the VGS, that the demarcation voltage of VDS goes closer and closer to the origin, right? So now if let's say I ask you what's going to happen if I join these demarcation voltage dots, right? If I join these demarcation voltage dots, I will get a curve. What will this curve look like, or rather what will this curve mean? I leave it up to you to figure it out, right? I leave it up to you to figure it out, and we can discuss this in the discussion session when we meet next. Okay, so I'm asking this. Find the equation of this curve. Okay, great. So Now, what was the motive of sketching all these plots? The motive was to find out y22, right? So what is y22 now? So y22, so let me, so y22 is del I2 del V2, which is nothing but del IDS del VDS, right, for a particular value of VGS, correct? So in saturation y22 is del IDS del VDS, where IDS is independent of VDS, right? So IDS is flat. In saturation, your IDS is flat, doesn't change with VDS, which means y22 is 0, right? What about in linear region? What is y22? Y22 will be del VDS of the linear region current equation. What is that? Mu n Cox W over L VGS minus threshold voltage times VDS minus half VDS squared, which is nothing but mu n Cox W over L VGS minus threshold voltage minus VDS. Okay. So now, what is the wish list for our amplifier? What should y22 be? Ideally, y22 should be 0, right, to get a good amplifier characteristics. Okay. So means that saturation region is good as far as the region of operation is concerned for our MOSFET, right? So this is, so just like what we concluded, to get large y21, we needed to get into saturation region with some condition. Similarly, to get small y22, which is 0 in our case, very good, that is the best I can do. We need to bias, we need to operate the MOSFET in saturation region, right? So for to get large y21, we need to operate the MOSFET in saturation region. To get small y22, also we need to operate the MOSFET in saturation region, right? So it seems like saturation region is the good region of operation in order to get the device operate in a manner in which the incremental parameters that we get are in the lines of an ideal two-port network, right? So which means that, to conclude, saturation region is the region of choice of a MOSFET to get amplification of power, right? Great. So now before we move on, there is a couple of jargons that we need to be accustomed to. So as it turns out, in a MOSFET, we don't call Y21 Y21, we call Y21 the transconductance or the GM, right? So Y21, we call it as GM. And what is the equation of Y21? Y21 equation is mu n Cox W over L VGS minus threshold voltage. One more piece of jargon. This VGS minus threshold voltage is often called the overdrive voltage, or VOV, right? So the reason we call it the overdrive voltage is because not only you need the VGS to be at least equal to the threshold voltage, you need VGS to be higher than the threshold voltage in order to get the MOSFET to work. So you need to have a drive on top of, on top of threshold voltage. You can assume the threshold voltage to be like a friction, right? A static friction, you need to at least give some force to get going, but in order to achieve certain velocity, you have to keep on applying more and more force. So the minimum force that you require, or minimum voltage that you require, is threshold voltage, and anything that you apply on top of threshold voltage is called overdrive, right? So that's why we call it VOV or V overdrive. The curious among you would also notice that, this equation can be written in multiple forms. If we notice that IDS is equal to mu n half of mu n Cox W over L VGS minus VT whole square, I can turn it around and say that this is equal to half mu n Cox W over L VGS minus threshold voltage whole square times 2 over VGS minus threshold voltage. This becomes ID. So this becomes 2ID over VGS minus threshold voltage, correct? So this becomes one expression for GM. This becomes another expression for GM. Similarly, if I eliminate VGS minus VTH, right? If I eliminate VGS minus VTH from this equation, I can also write it in the form of under root 2 mu n Cox W by L times ID, right? This is also an expression for GM, right? So you might wonder, right, what to do, which expression to use under what condition, or even more poignantly, are all of them giving us the right information, right? For example, you might look at the first equation and say that in order to increase GM, I need to increase the overdrive. I need to increase VGS minus VTH. But then if we look at the second equation, it looks like in order to increase GM, I have to reduce VGS minus VTH, right? And it looks like in the third equation, whatever I do to VGS minus VTH, GM doesn't change, right? It seems like all three equations are giving me three different intuitions, right? But here you have to be careful, and you have to understand that not only that all three equations are giving you the same information, because they have come from the same mother equation, right? They have come from the same mother equation of current in saturation region. And then the question arises that why it seems like they are different for these three different, why does it seem like the first equation, in case of a first equation, when I increase the overdrive, GM increases. In the second equation, I increase overdrive, the GM decreases. All you have to understand is the fact that in the first equation, or rather in the second equation, when you are implying that I am I am decreasing the threshold voltage, what are you doing to ID? Will ID remain constant? No, right? Because ID is a function of the overdrive, right? Or I should have, since I have used IDS everywhere, I should have used IDS here. So just to ensure that I am not abusing any notations, right? So IDS is a function of overdrive, right? So if you have set up your MOSFET in the way we have set it up, right? You have applied voltage at the between the gate and the source, right? And you have generated some current IDS, and you now say that I am changing VGS, but I will use the second equation and I will keep IDS same, whatever it was earlier. Then obviously you are doing something wrong, because you have to understand that moment you change VGS minus VTH, right, your IDS will also change, right? So similarly, if you say that, if looking at the third equation, it seems like if I change the VGS minus VTH, GM is not changing at all. Again, that interpretation will not be correct, because we know that if you change VGS minus VTH, right, if you change the overdrive, IDS will change. So all the informations are hidden inside the variables. They are embedded inside the variables. You need to know what will change, what might change, and what is constant, right? You might have a circuit in which the overdrive is constant. Overdrive will not change. You might have a circuit in which IDS is constant, or IDS will not change. So you have to choose your equations appropriately. Okay, great. So you will see this more and more as the course progresses, as to based on different configurations of circuit, one of these equations might be more useful than the other. Okay. So the final jargon for today's lecture is Y22. We call Y22 as GDS, right? And GDS is equal to 0 in saturation region, which is great for us, right? Okay, let's stop here. We'll start from we'll continue in the same way from the next class.